WinchBot 2.0 is the second iteration of my first WinchBot. The winches of my first prototype were driven by DC motors, using an Arduino Uno to build a closed loop system and a Raspberry Pi to do the coordinate transformation. The DC motors were replaced by bipolar stepper motors in version 1.5 by what the Arduino was no longer needed. The major change in version 2.0 is that I replaced the Raspberry Pi with the Simetic IoT 2020. Same as the Raspberry Pi, the IoT 2020 is a single board computer, however the Simetic ships with a sturdy plastics housing. Yocto Linux is the operating system running on the computer board. The arrangement of the GPIOs is identical to that of an Arduino Uno, so that the Simetic is compatible with countless shields, however I'm using the PON cables that are directly plugged into the sockets. Version 2.0 of my WinchBot was displayed on the stand of Aros Components on the SBS IPC Drives in Nuremberg, Germany, 2017. At the end of this video you can see what RS made of the sequences recorded on the first test run in Mörfelden-Walldorf, Germany. To do pick and place demonstrations I cut dies with an edge length of 30mm. Exhibitions are no isolated places as my video room, so I decided to use no more than 10 dies to build a tiny pyramid in Nuremberg. Back in my workshop I'd like to demonstrate that this robot is capable of stacking a lot more objects and so go higher than ever before. The building blocks are arranged on a tilted aluminum angle so that the dice slide to the bottom point. The endpoint of the aluminum angle defines the coordinates where the WinchBot can pick up new bricks. With two of the servos, the gripper can be rotated, so that the robot can grab a new cube. There were only minor changes on the hardware compared to version 1.5. I'm now using gears having 24 teeth on the motor shafts to speed up the WinchBot. An attempt with even larger gears having 36 teeth failed, caused by the lower torque on the winches. The robot started skipping steps. The maximum phase current of the stepper motors I'm using is 1.68A, while the Gecko drivers can deliver up to 3.5A, so you can try to use more powerful motors if you'd like to speed up this bot. However, you must consider special characteristics of the construction. The point where new bricks are picked up is close to one edge of the triangular frame. That's where the tension on the opposite cable is very low, causing vibrations when driving with full speed. That's why I'm reducing the speed of the winches close to that point. The variation in tension on the cables over all points in space is why the tendency to build up unwanted vibrations varies as well. Overall, this special robot works precisely considering the simple construction. WinchBot wasn't meant to become an industrial application, so that the low speed doesn't really matter. It was designed to be an educational tool. Being slow makes it more easy to understand how my WinchBot works. You don't need special tools, nor lots of time to make your own copy. There is no need to cut the aluminum bars of the triangular frame with high precision. The robot will work even with a warped frame. The conversion of the XYZ coordinates into cable length is an illustrative use case for the Pythagorean theorem and trigonometry. The software running on the Simetic IoT 2020 is almost identical to that of version 1.5, which was written for a Raspberry Pi. Only the subroutines for the stepper motor and servo control had to be changed slightly. I had to replace the lines containing the commands controlling the GPIOs. Changes were also made to initialize the GPIOs. All in all, only minor parts were replaced to adopt the software, and it was all done quickly. The web server Monkey is running on the IoT 2020 so that you can control the WinchBot using any computer running a browser. You can command the gripper to any point in space with the buttons and store coordinates in a text file. I only stored a couple of endpoints and used a simple text editor to add missing points of the large pyramid. Countless wireless hotspots are fighting for access on a large exhibition, which is why I used the Ethernet interface of the IoT 2020 to connect to the web server. The Edimax router also allows to use wireless network, and that works fine in my workshop. If needed, you can plug in a USB stick to add wireless functionality to the IoT 2020. I'm using a CTOP PSU100S with an output voltage of 12V at up to 14A to feed the Simatic and the stepper motors with electricity. The servos are connected to a second power supply with an output voltage of 5V at up to 3A. During the exhibition I used two inductive sensors to recalibrate the WinchBot from time to time while it was running. All GPIOs of the IoT 2020 were in use, which is why I connected the sensors to a BrainBox to observe their current state. The BrainBox type ED008 has 8 digital input-output pins that can be controlled by sending ASCII codes over the network. With that, only short cables are needed to connect the sensors with the BrainBox, while you can observe the state of the GPIOs through any distance using a computer network. Only 2 minor issues stopped WinchBot 2.0 from running during the exhibition days. One of the steel cables was fraying because I did not install it correctly, it did not run on the ball bearings. With a 60cm aluminum bar, my WinchBot was reinitialized quickly after replacing the cracked cable. Tricky to find was the second error. One of the steel cables seemed to get longer during operation, however the true failure was that a gear at one of the stepper motors came loose over time. Stepper motors itself are very reliable drives and they ran smoothly all over the 27 hours of operating time on the exhibition, same as the 3 servos, and as you can see, this robot still works fine. The special construction principle of my WinchBot attracted many visitors, and I had talks about how this robot works as well as what you could do with it in the future. Many thanks to RS Components for giving me the opportunity to display my WinchBot on their stand in Nuremberg. As you can see, WinchBot 2.0 stacks all of the dice in my video studio without any problem. After storing all coordinates in the text file, my robot had to build this pyramid multiple times to record all sequences of this video, and no failure occurred. Approximately 45 minutes passed by until the pyramid, made of 45 dice, is finished. The average time per brick is 1 minute. The base length of the pyramid is approximately 38cm, the height 27cm. With brick number 45, WinchBot 2.0 has accomplished its mission. You can get the parts list, circuit layout and software on my pages. Thanks for watching and I'll be back.